Hello dear students, I welcome you to NEET World. So today we will be discussing hydrocarbons, like continuation to the last session. So we will be having discussion on hydrocarbons. So yesterday we have discussed preparation and chemical and properties of alkanes, right? Okay, so there are some very important reactions like Woods reaction, coal base, electrolysis, then next decarboxylation reaction. All these things we have discussed in the last class, and we also seen some PYQs related to those concepts from NEET and EAPCET. Okay, so today we will be discussing few more topics from hydrocarbons. Okay, so let's start our topic with revision of last class. So alkanes. So where do we have what are the preparation methods we have? So using alkyl halides if we have, so like see alkyl bromide is there, so upon treating with something like lithium aluminum hydride or sodium borohydride, so it will be giving respect to alkane. So if it is methyl bromide, so we will be getting methane. If it is ethyl bromide, we will be getting ethane, like that. Okay, again similarly when we have alkyl halides, so upon treating with some zinc in acidic medium gives alkane. Okay, so these things we already discussed. Again Woods reaction here, alkyl halides with sodium in ether, so it will be giving coupling product, like if it is RCl, so we will be getting RR as a product. So if it is methyl chloride, we will be getting ethane as a product. If it is ethyl chloride, we will getting butane. So just couple that alkyl groups, that will be our alkane as a product. Okay, next, so Franklin synthesis, here we have alkyl halides with zinc. Okay, so 2 moles of alkyl halides we can take, so it will couple similar to Woods reaction, will give RR as a product. Okay, then next, here using Gilman's reagent, so this reaction is called Coriolis synthesis. So here we are using dialkyl lithium cuprate, which is called as Gilman's reagent. Upon treating with alkyl halide, we will be getting respect to alkane. So all these things we have discussed in the last class very clearly, right? So if you haven't watched those, we are session, so you can go and watch in the playlist, it will be there. So hydrocarbons, with the name hydrocarbons. Okay, next, so here, so alkenes upon treating with hydrogen in H2O2 gives respect to alkane. Then next, when we are hydrogenating, alkenes upon hydrogenation, I mean addition of H2 in presence of some metal catalyst like nickel, palladium, platinum we will be using, it will be giving alkanes as a product. Okay, if it is ethene, we will be getting ethane as a product. Similarly, alkanes also can be converted into alkanes by hydrogenation process. Okay, next, hydroboration, which we are going to discuss now. So hydroboration, it means to the alkene we are adding H2B6, I mean hydroboration we will be doing. So I will explain within some minutes about this reaction. Okay, so let's start our session. Okay, so before going to that, few more reactions are also there. So here Clemmensen reduction. So Clemmensen reduction is what? Ketones or aldehydes upon reducing, like using zinc amalgam and acid reagent HCl, like that, so we will be giving respect to alkane. So just conversion of this CO group into CH2 group, right? So if it is ketone, we will be getting if it is acetone, we will be getting product as a propane. For example, this is our ketone, let us say this is our ketone. So what is the name of this compound? It is acetone, right? So acetone, so when we treat with zinc amalgam and acidic medium, okay, we will be converting this CO group into CH2, it means CH3 as it is. Okay, then next here this CH3 is also as it is, and this carbonyl group, the center carbon, so it will be converting into CH2 form. So methylene group is formed from this carbonyl group. So this is what the conversion takes place in Clemmensen reduction as well as in Wolff-Kishner reduction. So Clemmensen reduction will be used in acidic medium and Wolff-Kishner reduction will be in basic medium. Okay, here we will be using hydrazine. I hope this is also clear. Okay, so one more important thing is carbides, like aluminum carbide, beryllium carbide upon hydrolysis. What I am saying, upon hydrolysis gives respect to alkane. So here when we have aluminum carbide and beryllium carbide, our product, the alkane formed here is, so these carbides upon hydrolysis gives methane as a major product. So what is the product formed upon hydrolysis of carbides, aluminum carbide and beryllium carbide? It is methane. So this is a standard question, you should remember like this. Okay, we can also have other carbide also, like calcium carbide. So calcium carbide will give see calcium carbide will gives, upon hydrolysis gives acetylene or ethane, you can say. So acetylene or ethane. So what is the common name? Acetylene, or IUPAC name we can say eth1ine. Okay, so this is a product. So you should remember, so different alkyne, different carbides will give different type of products. Aluminum carbide, beryllium carbide will give methane as a product. Okay, next calcium carbide will be giving acetylene or ethane as a product, and magnesium carbide will be giving propane as a product. What is a product? Propane is a product. When magnesium carbide is hydrolyzed, the product formed is propane. So write these statements. These are very, very useful and important also. Okay, next here, see what is this process, like soda lime. So what is the use of soda lime? So we can remove this CO2 gas, decarboxylation we can say na. So decarboxylation of carboxylic acid give respect to alkane. So here acetic acid is there, it means how many carbons are there? 2 carbons are there. So remove the CO2. So if you are removing the CO2, it means one carbon is removing, right? So what is the remaining alkyl group part? That alkyl group convert into respect to alkane. If it is methyl, it will be methane as a product. If it is ethyl, so ethane will be the product. Like that you should understand from the decarboxylation reactions. Okay, I hope this is also clear. Okay, so now tell me, I am writing ETOH. So what is our major product on decarboxylation? What is our product formed here? So when we are treating with soda lime, CaO plus NaOH. So what is the product formed here? So what I told you, the simple trick is just to remove this part, CO2 part. If you remove this, so ethyl with hydrogen. So you can just write it as ethane. So what is the alkane produced in this process? Ethane. So this is how you can remember. Okay, this is about decarboxylation. Next we have coal-based electrolysis. So in coal-based electrolysis, so yesterday we discussed complete mechanism and the important points regarding the coal-based electrolysis along with the PYQs. Now what you need to do is, again I am revising now. So just remove the CO2 part, this part. So whatever the alkyl group is there, double it. It means here we have methyl group now. So make methyl radical and methyl radical. So make a bond. So this will be the product. When it is methyl, we will be getting ethane. If it is ethyl, we will be getting butane. Like that. I hope it is clear. Just make the double of it. Okay. Again, reduction. So reduction of these alcohols, aldehydes, ketones, carboxylic acids using red phosphorus and HI will be giving respect to like alkane. I hope it is also clear. Next. So used based on this, you tell me, yesterday I given this question as a homework na. So tell me, identify the name of that reaction and what is the reagent used. Soda lime and decarboxylation. What is the thing used here? Soda lime means decarboxylation is nothing but NaOH plus CaO is used. Okay, and the next Clemmensen reduction. Just now we discussed na, Clemmensen reduction will be zinc amalgamate concentrated HCl. Next Wolff-Kishner reduction. Here we will be using hydrazine in basic medium. Yes, just now we discussed all these things also, along with, like in the yesterday's class also we discussed. So Wood's reaction will be using sodium in diethyl. That's it. So choose the option which is having this kind of option, A2. Only 2 options are there, remaining 2 eliminated. Next B1. So B1, only 1 option, so this one. 4th option is correct. C3, C4. Yeah, once again look back into the options. Okay, so here A2. So this one and this one. Yeah. The next B1. So B1, both are having B1. Yes. Next C4. C4 is only in option 2. So we have to go with option 2. And D3. So Wood's reaction D3. Yes. So option 2 is exactly the correct answer for this particular question. I hope it is clear. No confusions. So just go with the reagents with the respective name of that particular reaction. That will give our final answer. Then next we have correct order of boiling points of the following molecules. Yes. So these are physical properties, like based on the physical properties of alkanes question. So how can we say this? Boiling point of alkanes increases with increase of their molecular weight. One thing is molecular weight. So for a particular isomer, for a particular molecular weight containing compounds. For example, like you can say pentane, isopentane, like that. Okay, I mean same number of carbons should be present otherwise. Let's go like that. So you can say for isomers, so in case of isomers you can remember, like branching, see isomers, straight chain isomers have more boiling point than branched. So what I am saying, straight chain isomers will be having more boiling point than branched. It means as branching increases, boiling point decreases because surface area decreases. So larger or the more straight it is, so more surface area it will occupy, more boiling point it will be having. Therefore look here, so first one is N-hexane with maximum straight chain, and the next 2-methylpentane. So how can we write? Yeah, 1 2 3 4 5. 2 methyl means let us put one methyl group over here. This is 2-methylpentane now, so it is having one branch. Okay, the next, what about this? This is butane 2, 3. So I told you as branches increases, boiling point decreases. So which is having least boiling point, more branches are here, so it will be having least. So 3 least, the next 2, and highest is for 1. So 1 2 3. So 1 2 3 option 1. Yeah, this is how you can answer. So what I told you, boiling point decreases with increasing branch of that particular hydrocarbon for an isomer. Okay, so more branches, less boiling point for this third option. Less, like more straight chain it is, more surface area it occupies, therefore its boiling point will be high. Therefore first one will be having high boiling point. I hope it is clear. Next, chemical reaction. So chemical reactions of alkane. So alkane shows substitution reaction. What it will show? Substitution reactions. So what kind of substitution reaction especially it will shows? Free radical substitution reactions. So for example, methane is there. To this, if I add chlorine, so this reaction takes place in some sunlight or high temperatures are required. So here we will be getting different like mixture of products, like methyl chloride we may get, or see if we are taking this is limited amount. If methyl chloride is like chlorine is limited amount, this will be the product. It means this is excess, and this is limited. Therefore this will be the major product. This will be the major. Okay. In case if I take in reverse manner, if I take in this manner, CH4Cl2, this is excess and this is limiting. Therefore all the hydrogens are replaced by this chlorine and we will be getting CCl4 as the major product. So here I am writing major, means there will be mixture of products may also possible, but major products are this in these conditions. I hope it is clear. Okay, so write this. Okay, next. Yeah, so in this let us discuss more about this free radical substitution reactions here. So let us consider what is the reactivity of halogens here. So we have chlorination we can do, or fluorination, or bromination, or iodination. These are the halogens now. So here the reaction is more vigorous for fluorination, then next chlorination, bromination, iodination. So this fluorination is very violent, so that reaction cannot be handled in the laboratory. Therefore this fluorination is not preferred in this manner. In this method we cannot use fluorination most cases. Okay, and iodination is reversible, therefore we cannot use iodination also in fluorination, in free radical substitution mechanism. So here we will be preferring only for bromination and chlorination. So these two methods we will be preferring in this reaction, with this mechanism majorly. So alkanes, so this, let us take one random alkane. Okay, this is butane. So here it is, can be done with chlorination and we can also use it for bromination. Okay, so here condition is sunlight we have to use. Okay, so what are the products possible here? So how do we identify what are the products possible? See, I can write this as CH3, this is also CH3. See, this terminal methyl group, this terminal methyl groups are same, right? Okay, so replace one of this hydrogen with one chlorine, we are going to get one type of product. Both methyl groups are same only, na? So I am writing like this. Okay, I am replacing. See, substitution means what? We have to remove one atom or group and we need to replace some other group in that place. Okay, so I am replacing this hydrogen with some chlorine. Therefore, here I will be getting, so on this CH3 I removed one hydrogen, so it will be written as CH2. Now in place of one hydrogen I am writing chlorine. Yeah, so this is what is substitution process only, na? So like this is one type of product we can get, because this methyl group are same. So out of that I can remove one of the hydrogen from here or here, therefore we will be getting this kind of monohalogenated product. Similarly, here we have two hydrogens, here also we have two hydrogens. These two are also same type of hydrogens, because the environment, chemical environment is same. This side methyl group for this carbon also methyl group. Therefore, I can replace one of this hydrogen and I can write it as chlorine like this. So this is how the number of products we can expect. How many products are possible in this monochlorination or monobromination, they may ask. Similarly, for bromination also remove one hydrogen, replace with one bromine. Here also remove one hydrogen, replace with one bromine. So this is how you need to do. Okay, so this is about number of products formed, number of possible products in this particular monochlorinated or monohalogenated reaction. If they ask, you should answer it as like this. Okay, here one more thing. So here this is one product, here this is one product. So if they just ask normal structural isomers, you should say like this. If they ask total possible isomers including stereoisomers, if they mention, so here see, this is a chiral center here we have. It means this carbon is having 4 different groups, therefore it can be having 2 isomers. So chiral center is there, na? It means see, I can keep this fluorine, this chlorine either above the plane or below the plane. Therefore, 2 types of products are getting for this. So total possible isomers here for this particular compound is 2. So one is like above the plane one and another one is below the plane one. Therefore, so totally how many possible products? You should say 3 when they ask with including stereoisomers or optical isomers. You should answer like this. I hope it is clear. Okay, similarly same story works for this bromination also. Okay, now identify. So I will be giving a question. So number of possible monohalogenated products for this compound, so for chlorination, let us say including stereo, I am writing including stereo. So write the possible number of products and identify if they have any stereo center is there. So like take, if one stereo center is there, like use this formula 2 power n. If one stereo center is there, 2 power 1, so that will be 2 products will be formed. If 0 stereo center, only 1 product is considered. If 2 stereo centers are there, I mean chiral centers are there, 2 power 2, so 4 different products are getting like that. Okay, you just try to answer this question. I will be looking for your answer in the comment box. Okay, next. Okay, so what I told you, so we can chlorinate, we can do chlorination, and we can also do bromination using this free radical substitution mechanism. Na? So out of this, so I told you fluorination is more reactive, therefore we cannot handle that in the laboratory, so we are not preferring for fluorination, but we can do chlorination, which is more reactive than this bromination, and which is more reactive than iodination, which iodination is very slow. In order to do iodination, we need to use some oxidizing agents like HiO3 or HNO3, this kind of oxidizing agents we have to use here. Okay, so here for chlorination and bromination, which is more reactive? I am saying chlorination is more reactive. Okay, so now here chlorination is more reactive but less selective. Means see, more reactive means what? Wherever there is reactive site, there this chlorine go and react. Okay, but bromination is less reactive than chlorination. So what I am saying, bromination is less reactive and therefore it will selectively reacts at some particular sites. For example here I have some hydrocarbon like this. So for this I want to do chlorination, also I want to do bromination. Okay, so now tell me, what are the carbons here we have? These are the same type of carbons, right? So hydrogens present on this like carbons, like this pink color carbons are same, hydrogens are also same, and this one is a different one. So how many different types of carbons are there? So there are 4 types of carbons are there. Now see, this whatever I highlighted with pink color na, so those are of same type, of same nature. Okay, so now when these fluorination or chlorination or bromination is happening here, so we need to replace this hydrogen with one chlorine. So what are the expected products here? What are the possible products we will be getting? So I can remove one of this hydrogen and I can replace with one chlorine. Yes, this I can do here, here or here. So wherever I do, I will be getting this kind of product, one product like this. Similarly here if I remove this hydrogen and if I replace that with one chlorine, so we will be getting this kind of product. Okay, this kind of product. Yeah, so it is very simple. What we need to do is, in order to identify number of possible products, is identify number of types of carbon atoms are there, and on that number of hydrogens are there. I mean number of similar type or different type of hydrogens are there. See here, this carbon, this carbon, this carbon is same, therefore hydrogens present on these 3 carbons will be same. Therefore by replacing one of its hydrogen, we will be getting this kind of product. So if I replace from here or from here or from here, so all the 3 cases will give only one type of products. So this is of A type, let us say. So this is of A type of hydrogen, therefore product is A type, let us say. Okay, now this is different type of carbon and different type of hydrogen. No? Let us say this is B type of hydrogen, so we are getting this B type of product. Okay, like that. Okay, now one more thing I wanted to mention here. Bromination also gives like here one bromine. Okay, then next here also I can replace with one bromine, right? So these are the possible products we have. Okay, I hope it is clear. Same whatever I explained in the first case, same thing applies here also. In both cases we need to use sunlight. Okay, now what I told you, chlorination is more reactive, less selective. Okay, it means it vigorously reacts with whatever the hydrogens present here. So here 9 A type hydrogens are there na? So it means 9 A type hydrogens are there. So what is the degree of these carbons? It is of primary carbon na? It means how many, like for this carbon, how many carbons are attached? One carbon. So we can say primary carbon. So for primary carbon, the chlorination selectivity is this much. For primary carbon, chlorination selectivity is this much. Okay, if there is secondary carbon, that is 3.8 times. If it is tertiary, it is 5 times. Okay, so for bromination, I told you bromination is less reactive, more selective. It means bromination happens more selectively at tertiary. It means it will react 1600 times. Okay, then secondary carbon it will react with 82 times, and for primary if it is 1, then it will be 82, and this is 1600 times. I hope it is clear. So from using this table we can estimate or we can predict how much amount of A type product, how much percentage of B type product is formed. For example here, A type hydrogens are how many are there? 9 are there. So 9. So let us calculate it for bromination. So 9 into for each primary it will be having 1 time. So we will be getting A type product as 9. Okay, and for B we will be getting, so how many, this what kind of hydrogen it is? this is tertiary carbon na? So tertiary carbon, what is the selectivity? We have 1600 times. Okay, so how many hydrogens are there like that? So here we have only one. If there is 2, we have to multiply with 2 like that. So it will be 1600. So overall it is 1609. Okay, if I ask for percentage of B type product for bromination, so what you can do, the percentage of B type product is equals to total possibility in the denominator and possibility in for this particular type, that is 1600 into 100. Okay, so like this you have to do. Okay, so here we will be getting almost 99.9 percentage. It means what is the percentage of this product? It will be almost 99.9%. For this it is almost 0.1 around like that. So this is how you can predict how much amount of major minor product is formed. So what is a major product here? So this is a major product in this particular reaction, and this will be minor product. Similarly, if you calculate for chlorination, so you will be getting different types. So here in that for chlorination case, so this will be major, this will be major, this will be major, and this will be minor. So you can try by using this box. Okay, so this is the discussion on this free radical substitution reactions. Okay, I hope it is clear. If there is any doubt, you can ask me in the comment box. Next we have isomerization. It means for a straight chain alkane, for example like this, if we have a straight chain alkane, upon treating with AlCl3 like this, aluminum anhydrous aluminum chloride, so at some particular like 300 degrees Celsius, okay, so it will become a branched one. So straight chain converts into branched alkane. So this is what isomerization. So both are isomers now, structural isomers. This one and this one is structural isomer. This process is called isomerization. Okay, next, this is an important one again, aromatization. So when we have like a hexane, like hexane, 1, 2, 3, 4, 5, yeah, hexane. So upon treating with this oxide, chromium oxide and aluminium oxide, okay, at some 673 Kelvin to 773 Kelvin and high pressure. So what happens is, so how many carbons are there? 6 carbons are there, no? So it converts into respective aromatic compound. So 6 carbons, with 6 carbons we have like cyclohexane ring is formed, respect to hydrocarbon like aromatic ring is benzene. So like this, hexane converts into like respect to hydrocarbons aromatic compound benzene. Okay, if it is heptane, we can expect for toluene. So if it is heptane, 4, 5, 6, so we will be getting this as a product. Here methyl benzene or toluene is a product for aromatization of this heptane. Okay, next, if we are using some octane, so we can expect for ethyl benzene or orthoxide. So these are the like compounds you can remember for aromatization. So in aromatization what happens? A straight chain becomes aromatic compound, hexane becomes benzene, heptane becomes toluene, like that you can remember. So these conditions are also important. So reagent, whatever the thing they use, that is also important. Okay, next, okay, see here, red hot iron tube. So this also used for aromatization. So whenever we have like this, see, I mean, this is what you can say polymerization here. So this compound, like this we have now. So like that you just consider three compounds, 3 molecules. So this is one molecule and the other one is like this, and one more also you can consider like this. Okay, now aromatization will take place. See, so when we use this condition, so it happens like this, like this. So what we are getting? We are getting a 6-member closed loop. See, 1, 2, 3, 4, 5, 6 carbons are there. So 6-member cyclic chain is forming like this. Okay, now observe here, between 1 and 2 triple bond is there, but one is shifting for 2 to 3 connection, and remaining 2 bonds are there between 1 and 2. Let us write like that. and second carbon we have one methyl group, write as it is. Okay, next between 3 and 4 again triple bond is there, one is shifting and remaining 2 should be there like this. Okay, and fourth carbon we have one methyl group like this. Similarly here also between 5 and 6 we have like this and this one. So from this you need to just count number of sigma bonds. So how can you count the number of sigma bonds? It is easy, right? So whatever the pink lines you are seeing here, all are what? Sigma bonds only, and each methyl group is having 3 hydrogens like this. Okay, so here 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 like that. 12, this 3, 15 and this 3, 18. So total 18 is that correct? So I hope it is clear, right? Next, this is also simple. See, with what are x, y respectively in the following reaction sequence. Okay, so here what is the thing we need to use for this conversion? Just now I told you. So how many carbons are there here? 1, 2, 3, 4, 5, 6, 7. So when 7 carbons are converting into respective aromatic compound, toluene. So what is the thing we have to use here? So just now we have seen. Okay, so identify that from this again. So what is the next process happening here? So this toluene, treating with bromine and heating condition like sunlight or heat, I told you, for free radical substitution. So when we use this kind of condition, so here methyl group is there now. From this, one of the hydrogen is substituted by this bromine. So it means free radical substitution reaction takes place and gives us CH3Br like this. So like that product is formed. So our Y is, so here it is there, here also it is there. So what I told you for aromatization, what is the reagent we need to prefer? So Cr2O3 at 773 Kelvin. Yeah, so this is the most appropriate answer for this, because option C, the Y is there here and here. Before that, in the discussion of aromatization, I told you when like open chain is converted into aromatic compound, so like Cr2O3 is used at 673 to 773 Kelvin under high pressures, like at least they mention some pressure like 10 to 20 atms of pressure, atmospheric pressure. So this is what the condition required here. I hope it is clear. So option D is most correct for this purpose. Next, combustion. So we know hydrocarbons generally used as fuels, right? So the why they are used as fuels? Due to their high calorific value. Okay, so higher the calorific value, more efficient the fuel is. Okay, so let us say we have hydrocarbon CXHY is a hydrocarbon. So these upon combustion what we will be getting? We will be getting, upon combustion we will be getting complete combustion, I am saying, CO2 gas plus H2O. Like this the products will be formed. Now how many carbons are there? X number of carbons are there, we will be getting X CO2. So I just want to give you some hint how to balance this reaction, that is enough. So remaining thing you can refer the book. Okay, so X carbons, so all carbons will be converted into CO2. Again how many hydrogens are there? Y. So therefore here already 2 are there, so I am writing Y by 2 number of hydrogen atoms. See why I am writing Y by 2? So if I write Y by 2 into how many hydrogens are there here? Already here 2 it mentioned, so it means 2. So 2 cancel, we are getting Y number of hydrogens as like the reactant side, because here also Y number of hydrogens, product should also contain Y number of hydrogen, that's why I am writing Y by 2. I hope it is clear. Okay, then next thing, yeah, so carbons balanced, hydrogens balanced, the remaining thing should be oxygens now. How many oxygens are there here? See, 2x oxygen atoms here and here Y by 2 oxygen atoms here, right? So it means here it is molecule contain 2 oxygen atoms now. So it means what I am doing is 2x plus Y by 2 whole by 2 into O2. Why I am writing O2? Because here O2 molecule is there, that's why I divided here. Therefore we will be getting same number of oxygen atoms here and there. So just simplify this. Simplify if you do this. So we will be getting X plus Y by 4. So I am writing X plus Y by 4. So this is how you need to balance, or you can use this direct formula to balance in the reaction. Okay, then next let's move forward. So alkenes. So what are these alkenes? So alkenes are also like having carbon bond. Here it having one sigma bond and one pi bond like this. Okay, so simplest alkene possible is CH2 CH2 like this. Alkenes are also called as olefins because these are oily compounds. These are oily compounds, therefore they are called as olefins also. Okay, so oil forming compounds. Okay, so now, so what is the hybridization of each carbon here? It is sp2. For alkanes it is sp3. So there the carbon bond length in alkanes is 1.54 angstroms we can write. Okay, or 154 picometers we can write in alkanes. When it comes to alkenes, it is 1.34 angstroms or 134 picometers we can write. Okay, next. So what is the carbon like what is the hybridization of each carbon? It is sp2. Okay, next. Okay, what is the general formula of this alkenes? CnH2n. For alkanes, CnH2n plus 2. Okay, so for alkynes it will be CnH2n minus 2. Okay, the degree of unsaturation. What do we mean by degree of unsaturation? Number of pi bonds are there, na? So here we are writing like this, na, for simplest alkene. Here one pi bond is there, na? So that we can say 1 degree of unsaturation. It means if we remove this, like if we, by removing this we can add 2 hydrogens. So 2 hydrogens are equivalent to 1 degree of hydrogenation, 1 degree of unsaturation. So it has 1 pi bond, so I can say 1 degree of unsaturation. Okay, so this is having 1 degree of unsaturation du as 1. For alkynes degree of unsaturation is 2, for alkanes it is 0. Okay, for cycloalkanes again depending upon number of cycles it varies. For one cycle you can say 1 degree of unsaturation, or one ring you can say 1 degree of unsaturation. Okay, so what is the stability order? So what is the stability order of alkenes? Okay, so here I told you stability of alkenes is explained by hyperconjugation, right? When we are discussing about hyperconjugation we discussed it very clearly. So because more the number of alpha hydrogens, more is the stability of that particular alkene. So given this many alkenes are there, so in this, so whenever you are having some alkyl groups here, that alkene is more stable like this. So first this is completely substituted, therefore internal alkene or most substituted alkene is more stable than this unsubstituted alkene. Therefore this is more stable than this. See here 4 groups are substituted, but here one group is not substituted by any alkyl group, therefore it is less stable than this. Okay, now here 2 sides it is substituted, therefore this is having more stability, less stability than this, because it is having tri substitution, it is having only 2 substitution. Like that here we have trans form and cis form. So remember, trans alkenes are more stable than cis alkenes. Okay, see cis again, when it comes, cis means alkyl groups, same groups present on same side like that. Okay, here we have only one substitution there which is less stable than this 2 substituted alkene. Okay, now so what are the methods we have for preparation of alkenes? Okay, what are the methods we have for preparation of alkenes? Okay, from alkynes, first method is from alkynes. So by catalytic hydrogenation of alkenes, it means alkynes, when we treat this with H2 hydrogen, means hydrogenation only, using palladium. Okay, see H2PD CSCO3. So this combination is called Lindlar's catalyst. What is that? Lindlar's catalyst. Here what is the use of this quinoline? Quinoline act as catalytic poison. So what is the use? It is act as catalytic poison. It means, see, when we are adding this hydrogen to this alkyne, so it can undergo addition of 1 mole of hydrogen H2. For this double bond, one double bond will be replaced by 2 hydrogen, therefore we will be getting cis alkene. What is this? Cis, 2 hydrogen same side, 2 alkyl group same side, na? Okay, so this is called a cis alkene. So if we are not using this quinoline, we will be getting complete hydrogenated product. This is partially hydrogenated now. Only one double bond is replaced. One double bond is removed, and we are adding 2 hydrogens. One more pi bond, one out of 2 pi bonds, only 1 pi bond is removed by addition of this hydrogens, like 1 pi bond only hydrogenated. So I can say this is partially hydrogenated. So if I say complete hydrogenation, it means both 2 pi bonds can be removed. That is what complete hydrogenation. It gives alkane, but what we required only alkene, so that we are using a catalytic poison like quinoline. I hope it is clear. Lindlar's catalyst gives cis alkenes from alkynes. Okay, this statement also you should remember. Okay, when it comes to bridge reduction, so here we will be using sodium or alkali metal in liquid ammonia. So alkali metal in liquid ammonia converts alkynes to transalkenes. What it is doing? Transalkenes are getting from alkynes. So this also you should remember. These 2 things are very, very important. Alkynes with Lindlar's catalyst, that is what? H2PD CSCO3 quinoline gives cis alkenes. Okay, alkynes with liquid ammonia, alkynes with sodium metal or alkali metal in liquid ammonia gives transalkenes. So these 2 statements you should remember. Then next, okay, so there are some important reactions also there. See, like haloalkane is there, like alkyl group is there, halogen is there. Okay, so when we use alcoholic KOH, so elimination takes place and gives respect to alkane. So I will show you here. These are very important elimination reactions. Okay, listen here. So I am writing here, X is a halogen. Let us say this is chlorine or bromine or iodine, this kind of things. So here I am treating this with KOH. This is not aqueous, this is alcoholic KOH, and heating also required for this process. Okay, because we need to remove proton also. Okay, so this X, and see here one hydrogen is there, na? So the halogen attached carbon is alpha carbon, and the adjacent carbons are there, na? This one and this one. These are called beta carbons. So hydrogens present on beta carbons are called beta hydrogens. I hope it is clear. Okay, so now here alpha beta elimination takes place, or 1-2 elimination takes place, like halogen from alpha position, hydrogen as H plus proton from beta position, elimination takes place. Like this will take this proton, simultaneously this bond shift to the sigma star orbital of this sigma bond of this CX bond. Therefore this will be removed, like this, eliminated out. Therefore we will be getting a alkene product like this. So this is what happens in elimination reactions. I hope it is clear. Now you should get one more doubt. Sir, this is beta proton, this is also beta protons are there. So why can't we remove from here? Yes, we can also remove from here. So let's look what is the product formed in that case. So if I remove proton from here, so let us say this is the proton which we are wanted to remove now. So if we remove like this, so we are getting a alkene product like this. So out of these 2, which alkene is more stable? We know more stable alkene is more stable. So this is more stable alkene, therefore this is formed as major. This is formed as major, and this will be minor product. Okay, so now this product is called Sage-F product. What is that? Sage-F product. So what is the Sage-F product? So internal alkenes are major because these internal alkenes are more stable due to the hyperconjugation when we compare with the terminal alkanes. Terminal alkanes means this double bond at the terminal of this compound, but it is stabilized by hyperconjugation of these methyl groups. Therefore this is major. I hope it is clear. So internal alkenes formed major. Internal alkenes are major. So this is what the Sage-F rule. Okay, now this is called Hoffman product. This is what? Sage-F product. This is what? Hoffman product. So then when this kind of products are formed, yeah, so there is also possibility for that. So when we have a weak leaving group, For example, here I mentioned it can be chlorine, bromine, iodine, but I haven't mentioned it as fluorine. So what if it is fluorine? If it is fluorine, same reaction I am performing here, alcoholic KOH. Okay, what happens here? So the elimination takes place from this terminal side, therefore this will be seems to be major. When we have a weak leaving group, fluoride ion is weak leaving group, fluorine is weak leaving group, therefore when we have weak leaving group we will be getting Hoffman product as a major. This is what Hoffman product as a major when we have weak leaving group. And also when we use some bulky base, so what do we mean by bulky base? I will show you now. Bulky base, for example, here let us say I have here I have what chlorine is there. Okay, so for this what I am doing is, so for this, okay, let's replace this from here to here, that will be more effective. Okay, so like this we have here I am using alcoholic KOH and heating condition. So whenever you are seeing alcoholic KOH and heating, so blindly you can go for elimination. Okay, if it is aqueous KOH, so you can think of substitution reaction also. Okay, so what is the expected product here? So for this carbon, this is alpha to this chlorine, therefore alpha carbon, this should be the beta carbon, and this is also beta carbon, and this is also beta carbon, right? Okay, so we can remove this beta proton from here or from here or from this carbon from here also. Okay, so now if I remove these protons, product will be similar, that is what internal alkene. So therefore we can expect the product here as like this. Okay, now what about in this case when I am using tertiary butoxide, like this is a bulky base, look here how much big it is, like this. So this much bulky base, what happens here is, so due to its bulkiness it has like steric factors, so it cannot remove the proton from this most hindered side, it can be taking only from this terminal sides, very easy for this because of its bulkiness, therefore terminal alkene is formed, therefore we will be getting a product like this, like this. So when we use this normal strong base, this will be the major. If we use bulky base like this, this will be the major. Okay, I hope this is clear. Okay, I hope you will able to identify which is major, minor in this kind of cases. Yeah, this is what we discussed. Okay, similarly same story, elimination from alcohols also. By elimination of alcohol, by dehydration of alcohols gives alkenes, So here what are the reagents we can use? See, sulfuric acid can be used, or H3PO4 can be seen, sometimes P2O5 also seen, and Al2O3 at 350 degrees also seen. Okay, see here this alcoholic group, now when we treat with some dehydrating agent like P2O5 or concentrated sulfuric acid upon heating, so we can get this kind of product. See what happening here, so if this is the alcohol, to this, these are acid reagents now, so let us say H plus is added. See, alcohol and OH removed, as when we heat it, it will undergo dehydration, removal of water takes place, so that this bond is taken by this electronegative oxygen atom, therefore we are getting a positive charge on this this carbon, on this carbon. So when it is having this positive charge, okay, so what we can expect, this is primary carbocation which is least stable, right, which is least stable, therefore, okay, therefore, so if I shift one hydrogen from here to here, so what happens, so we can expect one hydrogen is shifted from here to there, like this. So we are getting a tertiary carbocation which is stable, primary or second tertiary. So we know tertiary carbocation is more stable. Therefore, this kind of intermediate is formed. So this process is called carbocation rearrangement by this hydride shift. Okay, which carbocation is more stable, primary or tertiary? Like tertiary is more stable. So this is formed. From this, now we have two possibilities. Removal of proton from here like this, it will be giving the product like this. Okay, this is a major, and removal of proton from here also, because this is beta for this carbocation beta, this is beta, this is also beta, this is also beta. From this two, this will be the product. From here only we can expect a product like this by removal of this proton. Okay, so this is what the minor, this is what the major. So these are the two possible products here. I hope it is clear. Okay, so what are the physical properties we have? So first three are gases, next up to 20 it is liquid, after that it is solid. Okay, so when it comes to dipole moment, cis will be having more dipole than the trans for alkenes. Okay, so next polar, more the dipole moment, more polar it will be having. So cis having more dipole moment than trans, therefore polarity is more for cis. Okay, melting point increases with increase in molecular weight. Okay, trans having more melting point than cis due to their close packing. In trans, packing will be like this, very close, therefore it will be having more packing, therefore more melting point. Similarly, when it comes to boiling point, increases with increase in melting point. Yes, so branching decreases the boiling point. If branching branching decreases so if more branching it is, less boiling point it will be having. Okay, so next boiling point is more for cis than the trans, like this. So solubility is more for cis than the trans. Okay, stability of trans alkenes is more than cis. So these are the basic things you can remember. Okay, so reactivity, I told you stability, more stable alkene is more substituted alkene is more stable. Okay, so reactivity inversely proportional to stability, more stable, less reactive. Okay, so which is more stable? This is more stable now, more substituted alkene. So this is more stable, therefore less reactive. This is less stable, more reactive. That is what the reactivity order given here. Okay, when it comes to cis and trans, we know trans alkene is more stable than this cis alkene. Therefore, trans alkene more stable, less reactive. That's why it is less reactive here. Next, what are the chemical reactions it can show? Addition, it can show addition, and then next oxidation, substitution, polymerization, isomerization. So about this, so in the next session we will be discussing about this particular reaction. See, substitution in alkanes we discussed, so we need to discuss about alkenes. Okay, in the next session we will be discussing about these reactions. So now let us see some questions, if there is any possible questions from this. So let me discuss here. Yeah, this is not done yet. Yeah, tell me for this, alkane that gives only one monochloro product on chlorination with chlorine. Okay, so here 2,2-dimethyl. So what I told you, in order to identify number of possible products, we just need to identify how many types of carbons or how many types of hydrogen atoms are present. So here for this, if I write 2,2-dimethyl butane, this is a butane, 2,2-dimethyl butane. 2,2-dimethyl butane having these three as one A type hydrogens, and here there is no hydrogen, here B type hydrogen, here C type hydrogen. So three possible products are possible. Monochlorination gives three different products. Like that you need to identify. For neopentane, the structure is like this. Yeah, so we are writing this. See, this methane group, this one, this one, this one. 4 different, 4 CM. So methane, no? So methyl group you should write. CH3, CH3, CH3. CH3, CH3, CH3. Yeah. So these 4 methyl groups are same. If you replace any of the hydrogen, will give same kind of product. So I can go monochlorination, only one product will be possible for neopentane, not for any of the other option, because other options will be giving multiple type of products. Like this you can solve. Okay, so the next thing is, yeah, so based on aromaticity concept which we have discussed, identify which among the following is not an aromatic compound. So directly go, first compound should be cyclic, next should be planar, right, the next complete conjugation, then next 4n plus 2 pi electron rule should be satisfied. So this will be satisfied by this thing. Here it is having sp3 carbon, therefore this is not aromatic, this is non-aromatic. For more clarity on aromatic compounds, there is a special video made with the topic name as aromatic compounds. Okay, just go and watch in the playlist, it will be there. Okay, after this, compound which obeys Huckel rule. Number of compounds obeys Huckel rule. Yes, that is obeyed by this. Next, this one also, and this is anti-aromatic compound. So ignore that. This is also anti-aromatic. This is aromatic. This is COT, cyclooctatetraene, which is non-planar. This is non-aromatic. So this is also not obeyed. So this is anthracene. Yes, that is also aromatic. So 1, 2, 3, 4. So you can answer with option 4. So you can go with fourth option. Yes. So I hope it is clear and it is helpful for your preparation. So if you have any doubts from hydrocarbons, so I will be discussing in the next session. So you can write in the comment box, so that I will check that and will update in the next class. So thank you for watching. Happy learning.